So today we're going to do Lagrange multipliers. This is yet another way of optimizing, of finding an optimal answer to some word problem. So we talked about that in section 14.7, which was a much more traditional, straightforward approach to optimization, where you take first derivatives, set them equal to 0. These are processes that are at least familiar to you from Calc 1. This Lagrange multiplier approach is completely different. It relies on a very straightforward geometric observation, and this geometric observation turns into a fairly powerful algebraic technique or process for optimizing a surface, optimizing a value according to certain constraints. And we've already been doing this, right? Gosh, I think maybe one of your web works was to find 3 numbers that added up to, I don't know, 50 or something, and whose product was a maximum. Yeah. Okay, so the thing that you're maximizing there is the product. What's the constraint? That they have to add up to whatever that was, 51, 52, what have you. Okay, so the problems are going to be very similar here. What this does is it provides you kind of a different avenue to get at the same result. So you can follow the traditional result of section 7, or you can follow this other slightly more sophisticated approach of section 8. Sometimes the techniques in 8, even though they both lead to the same place, sometimes the techniques in 7 you get bogged down in algebra, whereas the techniques in 8 don't, and vice versa. Sometimes the techniques in 8 get bogged down in algebra, and maybe the techniques in 7 will work. So it's just 2 different ways of attacking a problem, because in the real world, unlike in a calculus book, in the real world you're handed an optimization problem, and it's not part of some, it's the section on Lagrange multipliers, and so I go use Lagrange multipliers. That's not how it works in the real world. In the real world, you get this problem that you're trying to optimize, and you just start hacking away at it with everything that you know until you get it. And so now you're going to know 2 different ways of getting at this optimization result. Before I go there, however, any questions on what you're working on right now, web work? Lila?
I emailed you about web work 2, and you said to ask me.
Okay. So web work 2. Ah, yes. Such a strange little surface. You could make a chair out of it. Okay. So you're asked, these are good problems in my opinion, because one of the things I really like about this subject is it's a mixture of geometry and algebra and calculus, and you have to have some sort of real visual intuition. And so the intuition here, what we're trying to do is develop intuition for identifying maxima, minima, saddle points, etc. So a maximum or a minimum, they're fairly easy to spot. You're looking for places on the surface that are higher, at least in a little neighborhood, that are higher than everything around it. And you can see that there's clearly one here at the top of the surface. And you might also note that there's clearly a local minimum down here inside. So maybe those 2 are easy to pick off. I think the hardest thing to pick off in this particular surface is what's actually going on right down here at the low spot. When I first looked at this problem, I wasn't really sure what was going on down there, and I actually had to guess a couple of times myself. The question is, as I ride down this slope and hit the bottom here, does that bottom rise up a little bit and then drop down and then rise up again? Or does it just sort of smoothly go down to a minimum and then back up? That's actually an important question, and just by looking at it, I couldn't really tell. It seemed like it might rise back up and drop back down. Okay, and it's actually really important when you're counting maximums and minimums. Okay, it turns out that this guy doesn't rise up at the bottom there. It just comes down, drops to a minimum, and then goes back up. Okay. So if we accept that as fact, then what we have sitting right here is what? It's a saddle point, because as you ride along this ridge and you approach, you drop down and you bottom out, and then you go back up. That's great. So it's a minimum. But wait a second, as you go along this direction, it rises, it tops out and goes down. Oh, that's great, it's a maximum. Well, it can't be both. Or it can be both. It's called a saddle point. So that's a saddle point. And so the answer here was 1, 1, 1. But just for the sake of thinking a little bit more deeply about this, let's suppose that this little guy did rise up very slightly and then drop back down. Then what would this point be if it just rose up a little bit and dropped back down? It's going to be a max. So you'll have a max down here. You'll have the mins inside. You'll have that other max. So you have two maxes, one min, but you've introduced some saddle points. Two saddle points. So if this guy had risen up and dropped back down, then there'd be a saddle here and a saddle here. Okay? Okay. Other questions on web work? Oh, and let me just tell you a little bit of intuition. I mean, I think a couple of different ways to look at this, but one of the things you're doing is trying to look at places where the surface levels out in the x and the y direction. Okay? You're looking for a place where it levels out in the x, it levels out in the y. And then if the concavities agree, like if they're both concave down, then that's a strong hint that it's a maximum. If they're both concave up, then it's a minimum. And if they're mixed, like concave up, concave down, then that's a saddle point. So that's what I want you focusing on, is that not only the max and min, not only where the derivatives are 0, but the concavity. Other questions on web work? Yeah.
Can we do number 7?
Sure.
When I keep doing these, I get points that work when you plug them back into the constraint, and they keep passing the second derivative test, but for some reason it's not the one that...
Do you have the same numbers as me, 3, 4, 2? No? Oh, well. Did a lot of people have trouble with this one? I'm not sure I want to commit a whole lot of time to this, but I guess we can work one of these. So we want the coordinate. Let me ask you this. When you were doing it, were you minimizing distance squared or distance?
Distance. Well, I squared it.
You squared it. Good. Okay, so you weren't dealing with the square root. Okay, because one of the things that if you deal with the square root, you can lead yourself into some algebra errors. Okay, so find the coordinates of the point on the plane which is closest to the origin. So let's go and have a look at that. As sophisticated as this computer is, for some reason it can't automatically switch from one orientation to the other and pump it through to the, I guess I ask for too much. I'm spoiled. I mean, look at what I'm doing. Anyway. Oh, come on. Okay. This guy. So 3x plus 4y plus 2. And we want to minimize this guy. So is that what you were doing, roughly? Okay. So, oh, yeah. So what did you do first?
So first, to get rid of one of the variables in the distance formula, I solved for x, or sorry, z squared.
Yep.
And then plugged it into the formula.
Okay, so, and that's squared. All right, I would not square that out at this point. I don't know if you did that. Use the chain rule instead. 2, 3x plus 4y plus 2 times 3. And dy is 2y plus 8, 3x plus 4y plus 2, like that. Okay? I'm going to set both of these guys equal to 0, and this is what I was afraid of. I'm not sure I want to go into all this linear algebra stuff here.
Yeah, that's fine. I was just more wondering, like, I didn't know if there was like a conceptual
No, I mean, if this was your process,
Yeah,
your process
yeah,
is
that's what I
right.
did,
So you're going to get some candidates out of this. And, you know, you can probably just plug them into Z, but plug them into D. To find the min, or you can use the second derivative test.
So
Okay.
I did that, and I had the same numbers, and I got exactly the same equations, and still got the wrong answers.
Is that right?
And they came out nice too. It's -6 and 8 and 2. It's working.
Here, let me switch back to. Let's go back to Maple here. Okay, so don't look at this. There. So let's solve. And let me crank this up for you. So what do we have? 2x plus 6 times 3x plus 4y plus 2 equals 0, and 2y plus 8, 3x plus 4y plus 2 equals 0, and I want to solve for x and y. Is that what you got?
Nope.
Okay, so check your arithmetic.
3 times, I got different answers every time.
There you go. So write those down, and at least one person can check their work. Okay. Yeah, solving these linear systems is prone to error, so I'll try to keep it straightforward for the exams. But it's certainly worth, you know, cranking through and see if you can get the right answer. Okay. Hone that algebra. Rach.
So I assume that on tests you want us to use this whole long method even if you can just do it by taking.
You assume correctly, yes.
2 of the problems you can solve in like 3 seconds.
I'm going to be very clear about what approach I want you to take, okay? Because again, I totally understand that there are, in fact, I'm going to do an example today of Lagrange, using Lagrange multipliers, where if you look at it in the right way and think about it in the right way, it's much easier to do it this other way. But we're more talking about, we're trying to illustrate these methods and these deep geometric ideas, and not get you completely swamped in algebra. Because a lot of these ideas, even the ones in section 7, but also the one in section 8, these ideas are the foundation for computer algorithms for solving systems of equations. And you want to understand how these algorithms work so that you can use these computer systems in a way that's responsible. So without further ado, is there maybe one more question, web work? No? Okay, let me switch over to the thing that I was telling you to hide from earlier. You know that I like to stand out there in the middle of the floor there and pretend that I'm standing on the XY plane. You've seen me do that. Come on, thing. Wake up. And leading into today's lesson, I want to get us back into that perspective of I'm standing out here in the XY plane, X and Y values all around me, and above me is the surface. And I want to be able to switch back and forth between these two perspectives today so that we can do some of these optimization problems that I'm interested in. So here's the kind of the full-on perspective. I just made up this. Well, I didn't make it up, but I wanted just a nice, nasty surface that really would be difficult to deal with. The blue curve is me walking around in the xy plane, and the red curve is what's going on in the surface corresponding above. So if, for example, if I rotate this thing and I look directly down on this, come on, it's going to turn into that ellipse. Okay, but we know that when the ellipse goes up onto the surface, it gets all deformed and twisted, right? So the question of the day is, and in fact it was actually the question of the day on Wednesday as well. The question of the day is, if I restrict myself to the blue path, what's the largest value that I get on the surface? And if you look at this thing visually you see it's probably right in here, and possibly by symmetry, although we don't know that this is symmetric, but there might be a point here and a point here that are tied for top. You see that? And then there might be a point down here and a point down here that are tied for the bottom. Okay, so if you look back down in the xy plane, that might be right here. So if I plug in this value, then I'm going to go up to this maximum value. And if I plug in this value, I go up to this maximum value, right? And correspondingly, there may be something right here. I plug it in, I get that minimum value. And possibly over here, I plug it in and get the minimum value, because there are some symmetries. How do I find those values? How do I find the x and y values in the xy plane that when I plug them in, I get this maximum or these two maximums and these minimums? That's the question of the day. Okay. Really hard to figure out how you might do that from this picture, and so let me share with you another picture. Okay, these are the level curves of the complicated surface, and superimposed is the path that I'm interested in, this elliptical path when I walk around. And I'm asking the same question. As I walk around the path and I look up on the surface, what's the highest the surface gets and what's the lowest the surface gets? Okay, and it turns out that it's better to work with this thing in an editor for what I'm about to do. So I'm going to export this thing as a PDF file. And yeah, let's call it that and put it on the desktop. Okay. Okay. So there's level curves, and I'm going to open it with my PDF viewer and go to notebook mode. And let me motivate for you just a little bit more, 5 minutes or so, this big geometric observation. Okay, so up above this curve on the surface, things are really complicated. It's going up and it's going down, and we want to know where on the surface, where as I walk around this ellipse is it highest, and where as I walk around the ellipse is it lowest. Okay. These traces are level curves of the surface up above. So I've got the level curves, and I've got this constraint curve, which is what I'm going to start thinking of this thing as a constraint curve. What do you notice about the constraint curve and how it interacts with the level curves of the surface? Recognizing that the interesting points that I pointed out to you in the other figure are here, 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 here. And let me do some sketching on this thing while you're thinking. Bless you. Right, there might be another level curve right there, and maybe one right there, and possibly one right in there. Are you getting the hint? Right. These are not all of the level curves for this surface. It's just a sampling of level curves. Right? There's actually an infinite number of them, and they fill up the whole plane. So what we're looking at here is just Maple's selection of level curves for this function. So there's clearly a level curve in here that might follow that kind of trajectory, and there's another one here, and another one here, and another one here. What do you notice about those curves with respect to the constraint curve in blue? They appear to be tangent, and that's the big geometric observation, that the candidates, the places where there might be a maximum or a minimum, are going to be places where the constraint curve is tangent to a level curve of the function. And that's what's going on right here. And there's nothing special about the ellipse. What if I wanted to find the maximum along some line in the xy plane? It's probably going to be, let's see, probably going to be maybe right in there. There might be one right there. That's pretty fortuitous.
Right, then it going to be at like 1,2.
1,2. So 1,2, like right in here.
Yeah, because isn't that level curve higher than the other?
Okay, so what I'm looking for is places where the red line is tangent to a level curve. So maybe right here, maybe right here. But you can see there are other places where it crosses the level curves at a big angle, right? And that's where, and think about what's going on here. Okay, we don't really know whether this is uphill or downhill, but let's pretend this is uphill. So here I am, I'm moving on the constraint curve, and I'm looking up above at the surface. Is the surface rising? Sure, it's still rising, it's still rising, it's still rising. Right? Maybe it starts to fall here, starts to fall here. Right here, though, I travel along the level curve for a little while. And that's a place where there might be a maximum or a minimum along the level curve even.
So if you had like a cone and then you had a line that didn't have a maximum that was lying tangent to like an infinite number of curves, wouldn't none of them be maximum? Or not an infinite number of level curves?
Well, without getting into too much detail, all we're finding are candidates here. Okay. So it might be that one of the candidates is not a max or a min. Okay, so let's just leave it at that. There are a lot of possibilities. The thing I want us to focus on here is just in sort of the plain vanilla sense where these guys might be tangent to level curves. So maybe, you know, what if I don't know. How about if I came in along something like that? I bet there's even one right in here. That's terrible. I bet there's one right in here, though, that'll get it for you. Anyway, that's the point. So we'll just stick with the big picture and not get mired down into the details here. We're looking for places where the constraint curve is tangent to some level curve. That's the big geometric observation. Now, how do we make that happen algebraically? Well, we know, I think it was in section 5, we came up with a quantity that was perpendicular to level curves. Remember what that was? Gradient? Yeah, the gradient at a point is perpendicular to the level curve of the function through that point. So we've got the gradient here. Maybe it points, we've got gradients here all around. Let's put one in here. Right, this guy has gradients sticking out all around, perpendicular. And this guy has gradients all around. Right, so the gradients are everywhere. And what we're trying to do is get the gradients to line up. So here's some that are kind of close together. Let me get rid of that guy. Yeah, get that out of the way. Okay. So here's a gradient right here. And maybe along this curve here you can see there's one. Maybe there's a curve through here and a gradient here. What we want to try to do is get those guys to line up. Find the places where they line up. Okay. What does it mean for two vectors to be parallel? Do we have a test for that. We know that the cross product of those two vectors will be 0. Or we can note that one vector is a scalar multiple of the other vector. All right, either one of those are ways of telling whether two vectors are parallel. So these curves are going to be tangent when their gradient vectors are parallel. All right, so let's talk about what that means. So the method of Lagrange is to note that optimizers occur where gradients align. So let's say we're trying to optimize some function f of xy according to the constraint g of xy equals some constant c. This is all going to be much clearer when I do the first example. So just bear with me. Suppose I want to optimize f of xy according to some constraint g equals c. That's exactly what was going on in the first picture here. So so in the first picture here, wow. I give up. Yeah, I even lost it. Okay. In that first picture here, the constraint was the blue curve, and the function that we were trying to optimize was the big wavy surface. Okay, so let's go back to notes here, and what we noticed was when that constraint curve was tangent to a level curve, that was a place where there might be a maximum or a minimum. And we note here that gradients are always perpendicular to level curves, so what we want to do is get gradients to line up. So we want the gradient of f to be equal to some scalar multiple of the gradient of g. And this lambda, you know, we don't really care too much about it. It's called the Lagrange multiplier. And we're not really interested in what that lambda actually is. All we're really interested in is the x and y values where those guys line up. So lambda is sort of this extra helper parameter which helps us through the calculations, but really doesn't play a role in the final answer, if that makes any sense. Okay, you'll see how it works in this first example. So, at what point on the circle the unit circle at the origin, is the product xy a maximum? Fairly straightforward question, simply stated. What's the thing that I'm trying to maximize in this problem?
X times Y.
Mm-hmm. Now, if I didn't have the constraint, what would the answer be? Infinity times infinity. Sounds like fifth graders arguing. Okay, so yeah. And you say infinity squared times infinity squared. Okay. Yeah, without the constraint, this is not an interesting question. With the constraint, it's actually mildly interesting. So now you're stuck on the unit circle. Which two coordinates, which pair of coordinates on the unit circle, when you multiply them together, gives you the largest product? Well, give me a point on the unit circle. Well, root 2 over 2, root 2 over 2, you mean?
Oh, okay.
Yeah. So root 2 over 2, root 2 over 2, which corresponds to the point at pi over 4, or with angle pi over 4. What's the product of those two guys? 1/2? 1/2. I know it's hard. It's late Friday afternoon. 1/2. Give me another point on the unit circle.
0, 1.
0, 1. What's the product? 0. So that one doesn't win. So far, root 2 over 2.
Let's just keep going. All the points.
Right, so we could just try all the points. The other one I guess of slight interest would be root 3 over 2 times 1/2, which is root 3 over 4. Bigger or less than 1/2? Less. Okay. So that's not a winner. Right now the winner appears to be root 2 over 2, root 2 over 2. Right? And probably everybody in this room believes that that is the actual winner. Right? There's some...
Negative.
Okay, that's one of the winners. It can't be beaten, let's put it that way. Okay. And there's a certain elegance to that solution, right? Where they're equal and there's a lot of symmetry in that result. And you would certainly not expect, you wouldn't really expect anything else. The method of Lagrange multipliers can handle this kind of problem fairly easily. So what's the thing that we're trying to maximize? That's what we're always going to call f. So in this case, it's the product xy. And what's the constraint curve? Well, the constraint curve is a level curve of g of x, y equals x squared plus y squared. Okay, and we're always going to call that function g. So there's a subtlety here, right? The constraint curve is a level curve of g. G is the thing that we want. All right. Now, we know that there are candidates for optimization when the gradient of f is equal to some scalar times the gradient of g. Candidates for optimizers can be found by solving that equation. What's the gradient of f? It's a vector of first partials. Y comma x, good. Times lambda, equals lambda times, what's the gradient of g? 2x, 2y, good. One vector equation, actually two scalar equations. y is equal to 2 lambda 2x, or 2 lambda x, and x is equal to 2 lambda y. So there's two equations, but there's three unknowns, which we don't really like so much. But there's actually a third equation. So now we kind of have three equations. Well, we do have three equations, three unknowns, which makes us feel a little better. Doesn't mean that there's a solution, right? Because these are nonlinear. This is a nonlinear system of equations, and you know you can get all kinds of crazy behavior out of such systems of equations. And I have to tell you, as beginning Lagrange multiplier students, this is where things tend to go off the rails for such students. You get these three equations, and now you have to try to find x and y in particular. Lambda's not so important, but you have to find x and y. And I wish I could give you some recipes. I will try to give you some tips on how to go about, you know, what are some things that work. But a lot of times there's going to be some dead ends, right? You're going to try to solve for x and substitute it into the other equation, and then solve for y or whatever. And things are going to break down, and you're going to get frustrated and pound your head against the wall and things like that. Just keep plugging away. Do as many of these things as you can by hand, and what you're going to do is start developing an intuition for these nonlinear systems of equations, and I promise that you'll get better and faster at it if you do the work. Okay, but the first few of them are going to be a little free form, a little bit frustrating possibly. So I've got three equations, three unknowns, and I don't care a whole lot about lambda other than just as a vehicle for manipulating these expressions. But one possible way to go is to solve for lambda everywhere that you can. So for example, we might have lambda equal y over 2x and lambda equal x over 2y. And we might be a little bit concerned about x being 0 or y being 0, but we can rationalize that away. How? You're not going to maximize the product using 0, right? So we don't have to worry about. So you just want to be careful while you're doing your algebraic manipulations and dividing things out that you're not losing solutions. And by dividing here, I'm not losing a solution. Set the lambdas equal to, set these two expressions equal to each other. So y over 2x equals x over 2y. And where does that get me? It gets me y squared equals x squared. You could take the square root of this thing and then start worrying about pluses and minuses and things like that. But I recommend that you put that off as far into the future as you can. And it turns out in this case you can put it off because we're about to go, so we've eliminated lambda. We're about to go over and solve for x and y. And we've got this equation, and we've got this one that we haven't used yet. What would be a good thing to do that might also avoid square roots? I can just drop y squared equals x squared into that constraint equation. So don't forget about the constraint equation. So if I do that, I get x squared plus x squared equals 1. Or 2x squared equals 1, or x squared equals 1/2, or x equals what? Now I need to take a square root. How many solutions? It's actually 1 over the square root of 2, which is the same as root 2 over 2, right? Reassuring. This is what we expected. If x equals root 2 over 2, what's y? Let me be a little... Then y squared is equal to what? 1/2. And y is equal to plus or minus root 2 over 2. Okay, so I just want to be really careful about this process because corresponding to this solution, there are 2 y values. So I'm going to get 2 candidates from that one solution. What if x is equal to negative root 2 over 2? Then y squared is equal to 1/2, and what's y? Same thing. And from that other value of x, I get 2 more solutions. So there's a total of 4 candidates. What do I do with the 4 candidates? Go ahead, Rach.
Plug them into the FX.
Plug them into the thing that I'm trying to maximize, exactly. Let's see which one is biggest. Which one is biggest? So the maxes are the positive ones and the negative ones. And what about the other ones? Those are the places where the minimums occur. And in those cases, they're minus 1/2. The product is minus 1/2. Okay. So you can say some interesting things here. You can say that the product of coordinates on the unit circle is always between what and what? Negative 1/2 and 1/2. Or you can say something like this. You can say that the absolute value of xy is less than 1/2, less than or equal to 1/2 on x squared plus y squared equals 1. You can say something like that. Okay. Let's do another one. So here I was optimizing a function of 2 variables. I'd like to optimize a function of 3 variables, and it turns out that the same process applies. So let's look at, let's find points on the sphere x squared plus y squared plus z squared equals 36 that are closest and farthest from 1 to 2. Okay, so we've got a sphere. And this sphere is centered at the origin and has radius 6. If I want to draw a nice general picture, probably the first thing I should figure out is where this point is with respect to the sphere. Where is this point with respect to the sphere? It is. It's actually inside. How do you know that it's inside? It's less than 6 units from the origin. How do you know that? Well, 1 squared plus 2 squared plus 2 squared is 9. Take the square root, it's 3. Okay, so this point is somewhere kind of halfway between the center and the exterior. Okay. Does everybody see that there are going to be points on the sphere that are closest to this point and points on the sphere that are going to be farthest away? In fact, the point closest is probably going to be somewhere out here, and the point furthest away is probably going to be back in here somewhere, right? And you can probably even guess how those points are related to each other on the sphere, right? They're what are called antipodal points. They're as far apart from each other as they can get on the sphere. For example, the North Pole and the South Pole are antipodal points. These guys aren't North Pole and South Pole, but they are as far apart as they can get. There are other ways to solve this, admittedly, but we're going to do it using Lagrange multipliers. Yes?
Will we ever actually calculate the Lagrange multiplier, or is it just kind of like a thing you put in just to say that these
Okay, so
vectors are equal?
that's an excellent question. We are never, at the end of the problem, we're never interested in what lambda was. But during the problem, even though in the previous exercise I actually set the two equations equal to each other and lambda went away and I never bothered with it again, there are cases where it's useful to find lambda during that process and use it. And I think one of my exercises today actually does that, but not this one. Okay, so let's find these points and see if we can't confirm our intuition about these points. In fact, I think if you think hard enough about this, you can figure out what these points are without going through this nasty process. For example, if you take the vector from the origin out to there, so that's exactly right. So the magnitude of that vector is 3. If you double it, you're going to be on the surface of the sphere. And if you multiply that thing by a minus sign and go backwards through the origin, you're going to find the other point. So can you figure out what this point is? 2, 4, 4. Done. And this guy? Very good.
That only works because the point happens to be halfway between origins.
Yeah, but it's still doable, right? All you have to do is figure out how far the thing is from the origin, right? That's a scalar, and then exactly. So and just scale it correctly. So it did happen to be extra convenient, but the process would work for any point. Okay, so let's go through this. So the thing that we're trying to optimize is the distance squared, right? Remember I said to use distance squared whenever possible? Oops. And I'm trying to optimize the distance from this point. So there's a generic distance function to the point 1, 2, 2. Again, it doesn't make sense to try to optimize this function in the absence of a constraint, because I can get as close to this point as I want by choosing the point itself, and I can get as far away from this point as I want by just heading off to infinity. So we have to have a constraint, and I called it D and I meant to call it F. The constraint is what?
Sphere.
It's the sphere. And the sphere is a level curve or a level set of this function, right? So the constraint is a level set of G. And the method of Lagrange multipliers says we want the gradient of f to be equal to lambda times the gradient of g. In other words, we want the gradient of f and the gradient of g to point in the same direction. They may differ by a scalar, but they point in the same direction.
I understand that if you're taking the derivatives, it doesn't really matter, but what happens at 36? Like g is...
Well, that's an excellent question. What role is 36 playing in this setup?
I mean, it's pretty huge.
So it's not really playing a role in this particular
Part of the equation.
part of it will play a role when we start solving the equations, you know, with lambda and x and y and z and so forth. But the reason that 36 is not here is because I'm not interested in, at this point, I'm not interested in that constraint surface. I'm interested in the function whose level curve is that surface. Because it's the gradient of that function that is perpendicular to that level surface. I know. Think about it. What's the gradient of f? Yeah? Okay. Times lambda. Gradient of g. Okay. Instead of 2 equations like we had in the last example, we've got 3 equations from this particular step. And the 2's are going to go away. Does everybody see how the 2's can go away? So we get x minus 1 equals lambda x. Y minus 2 equals lambda y. Z minus 2 equals lambda z. All right. Again, oh, and there's also the constraint equation, x squared plus y squared plus z squared equals 36. Okay, again, this is where things can kind of go off the rails. You just got to muck around with it and play around with it, and the goal here is to essentially eliminate 2 of these variables. So play around with these guys and see if you can eliminate 2 of those variables. One way to do that would be, for example, to express y as a function of x and z as a function of x. Again, these are just general suggestions. Sometimes they work, a lot of times they work, sometimes you have to be more clever. Okay. Right, what do I mean by more clever? I'll try to give you an example here. So I said try to find y as a function of x and z as a function of x. If you can do that, then the constraint equation just turns into a simple equation in x, which you could solve. Sometimes it might be really difficult to find that, but what you might do when you're mucking around over here is you might discover that x squared plus z squared is equal to, that y squared plus z squared is equal to x squared for some strange reason. You might discover that. If you do, then you have x squared plus x squared equals 36, and you got something that you can solve again. So keep an eye out for things like that too, sort of serendipitous expressions that pop up that you can use to eliminate variables. But here we're just going to plug away here and see what happens. Let's solve for lambda, and I'm going to label these guys 1, 2, 3. And I don't remember how I did this one, so let me just wing it here. Let's try that. And maybe that. Oh, it's coming back to me. Okay. X minus 1 over x equals y minus 2 over y. Multiply both sides. xy minus y equals xy minus 2x. Does everybody see how I got that? There's a nice cancellation. And what we get is y is equal to 2x. Yeah, you'll not be surprised to learn that if I combine 1 and 3, I'll get z equals 2x. So I'll let you work that out. So here's a case where I managed to express y as a function of x and z as a function of x. Take these guys and trot them on over to the constraint equation. Okay? X is equal to plus or minus 2. If x equals 2, then y is 4 and z is 4. If x equals minus 2, then y is equal to minus 4 and z is equal to minus 4, which is exactly what we thought. From our earlier discussions, we know that the positive one is the shortest distance and the negative one is the longest distance. But what if you weren't sure? How could you figure out which one is the maximizer and which one is the minimizer? Just dump it back into the thing that we were trying to minimize. Exactly. So this is the minimizer. This is the maximizer. And if unsure, plug into D, not D, F. And compare. Somebody had a hand up? No? You're good? All right. Questions on this? Okay, I'm going to finish up with a slightly wordier word problem. Not too much wordier, but oh, and it's an exercise from the book. So let's go look at the book here. At least I'm consistent. I did that 2 hours ago. Okay. Number 6. Okay. The material for an aquarium, for the bottom of an aquarium, costs half as much as the side material. This is an open-topped rectangular glass aquarium. Find the shape of the cheapest aquarium that holds a given volume. You know, classic contrived manufacturing problem for calculus. But you know, we'll see how it goes. So we've got this aquarium. And maybe it's got some stuff going on back here, I don't know. Okay, let's give ourselves some dimensions. We've got an open top and an expensive bottom. No, cheap bottom.
Yeah.
Cheap bottom. Okay. The constraint is, well, let's look at this thing. The material for the bottom of an aquarium costs half as much, yada, yada, yada. Find the shape of, what's the constraint? Sorry? Cost is the constraint. And, sorry? Oh, no, you're right. Cost is the thing that we're optimizing. What's the constraint? Volume is the constraint, right? We want a specific volume, V in this case. So they're not going to give you some absolute, 30 gallons or something like that. They're just going to say V, solve it for some general V. Yeah, and the thing that we're trying to optimize is the cost. Okay, so we did a problem similar to this on Wednesday. The constraint here, v is x times y times z. And we did a similar problem here where we're just trying to minimize the amount of material. I think it's good to start there and then just tweak. So to minimize material, we can minimize surface area. And to minimize surface area, you have to build a surface area formula. And a surface area formula for this guy would be x times y for the bottom plus 2 times x times z for the front and back plus 2 times y times z for the left and right. But you can't just use this guy. Is that your ladybug? But you can't just use this this guy as is, because it doesn't take into account the fact that the bottom is half as expensive as the sides. How can I tweak this guy to make that happen?
Well, first off, can you like equate y and z? Because never mind. To do that everywhere that there's an x, you do 2x.
Go ahead, Sarah.
If you make, instead of surface area, do price, and then multiply the bits of the equation that are for the sides by 2, so that price is expensive as the bits for the bottom.
Or I could just put a half there.
Or you could
Yeah, there you go. Okay.
But 4
We have a fraction fear. No. Okay, so you can put a half there. Okay, or you can put a 1 there and put 4s on the other one. I'm going to put a half there. So, and I don't know what happened with my screen there. That's a Z. It's not helping, I know. Okay. This is the thing that we want to optimize, and we have the constraint. So f is x, y, z, and g. I'm sorry, did that exactly backwards. F is 1/2 xy plus 2xz plus 2yz, and g is x, y, z. And again, I'm just going to keep noting this until it sinks in, that the constraint is a level set of g, right? So how do I get the constraint? I take g and I set it equal to v. That gives me a level surface. That's the constraint. Okay, how do we start a Lagrange multiplier problem? We just start with getting the gradients to line up. Let's see, the gradient of f. That's the partial of f with respect to x. So that's 1/2 y plus 2z. With respect to y, 1/2 x plus 2z. With respect to z, 2x plus 2y. Has to equal lambda times the gradient of g. The gradient of g is the derivative with respect to x, derivative with respect to y, derivative with respect to z. I've got 3 equations plus the constraint equation. Now, in the earlier hour, as I was screwing around with these equations, I came up with a really quick shortcut that I have no idea. I don't remember what it was now, so we'll just see what happens. So this could be really slick or it could be really painful. X, Y, Z equals V. That's the constraint equation. Oh, I remember. Okay, good. Okay, solve for lambda. In 1 and 2. So if I do that, I get 1 over 2z plus 2 over y. And I get 1 over 2z plus 2 over x. And yes, those two together tell me something. What do they tell me? X equals y. Right? If I set them equal to each other, the 1 over 2 z's cancel. And I get x equals y. Does everybody see that? Okay, good. I think when I did it in my office earlier in the day, I went really the long way. And then I got to this point and somebody said, hey, x equals y. And I said, really? And they were right. Okay. So yeah, even at my advanced age, probably because of my advanced age, I can go down some dead ends and give myself more work than is necessary for some of these equations. So just be warned that when you get to this point, it can get messy.
Couldn't you have started the problem by like using the fact that the smallest surface area per the smallest area per like length times width is xx, and so you could have had x. You could have started out by saying x equals y.
Well, I don't know that a priori, other than just your words.
Okay.
And so what I'm trying to do is have sort of a rock-solid mathematical foundation where I don't have to argue with the manufacturer. I can just say, here you go. Okay. All right, so x equals y. That's good because that would let me eliminate one variable. I still need to eliminate another variable. Ideas. So I know x equals y.
Plug it into lambda, or plug it into 3 to get lambda.
That's exactly right. So take this guy and go into 3. Why? I don't know. Just because it works. Okay, and that's where we're headed here, people. So just be prepared for that. So is that right? So if I plug that into 3, I get 4x equals lambda x squared. Lambda is equal to 4 over x. I'm totally ignoring dividing by 0 here, so I'm going to let you deal with that also for the sake of time. Lambda equals 4 over x. Helpful? Not helpful? What I'd really, the promised land here would be z as a function of x, right? Nick?
Well, it doesn't really help very much.
It does.
But if you put if you put it into 2, put lambda into 2, and then if you put the x equals 1 into 2, you can get an equation that only has z and y.
Well,
You're on the right track.
If you plug
Okay,
in-
and for the sake of
Oh, no,
time,
wait.
If you plug into
No,
2,
you can just have.
Just take this and put it here.
Oh. Didn't you plug it back into it?
So if I take that, put it there, then what I get is 1 over 2z is equal to, what, 2 over x? Or, oh good lord, x equals 4z, or z equals x over 4. Now I have y is equal to x, I have z is equal to x over 4. I'm not going to finish this off because we're out of time, but where do I go? Plug them in up there, solve for x, solve for y, solve for z. Let me just show you what the answer looks like so that you believe perhaps that it's reasonable. Cube roots. That makes sense, right? Okay. Have a nice 4-day weekend. See you Wednesday.
Oh.